I trust the previous example was enjoyable. In this video we'll take the knowledge acquired from the previous video and develop a slightly more complicated structure, namely a pin-jointed truss. What we set out to achieve in the video is the following: working with multiple members, load cases and section types, as well as ensuring the member joints represent the structural intent. The first bullet point, working with multiple members, is crucial because the insufficient attention to numbering is a source for most bugs. When numbering isn't sequential, when a number repeats itself, analysis errors and/or incorrect structure definitions occur. We want to, in this example, define a simple truss as shown on the right. When it comes to node creation, first we need to define some key parameters of our structure. The span of the truss is equal to 6 meters, the height 1,75, and the number of nodes equal to 7. For this, we define variables s, h, and n respectively. When it comes to the algorithm for defining the nodes, here we create a simple for loop and loop over the number of the nodes, which is a known value. I is therefore sequential and is suitably our node tags. We also need to define our x, y, and z coordinates. The x coordinate increases sequentially from 0 to the length of the truss. Here a suitable formula can be given. All y coordinates are 0 since we are defining a planar truss. And in terms of our z coordinates, all odd numbered nodes have a z value of 0, while all even numbered nodes have a z value equal to the height of the truss. We can, by default, set all z values to 0 and manipulate the appropriate nodes by filtering for the even node numbers using the Python modulo operator. When it comes to members, let's now define 3 sections, all with the same material. These definitions were already covered in the previous video, and we are advancing on our knowledge here by defining 3 section types, one for the diagonals, one for the bottom chord, and one for the top chord. We can use a comment to distinguish the different section types. Now for the algorithm for modeling the beams. Note, there are many options to do this. For small structures we can define each point and member explicitly, so-called hard coding. However, the bigger the structure gets, the more tedious this becomes. Therefore, we want to try to follow an ordered numbering procedure, such as the one shown. We know that even numbered nodes lie on the top chord, and odd numbers lie on the bottom chord. Here we can see how easy it is to make errors in node numbering. A good tip to test your numbering algorithm is to print the element numbers to the console to make sure it is sequential and without gaps. We start by defining a variable for our member tag. This will be incremented within our appropriate for loop. Here we will again loop over all nodes in the structure. If a node is odd, we can define both the diagonal and bottom chord. For our diagonal, the start node is the node number, and the end node is simply the node number plus 1. For a bottom chord, the start node is also the node number, and the end node is simply the node number plus 2. Note, we need to increase the member tag before each member call. Finally, the loop should ignore the final node. We can include this in our conditional. A similar approach is applied for the top chord. Except we deal with even node numbers and not odd numbers. Furthermore, we want the loop to ignore the final even number, which is 6. Because we ignored the final even node number, we still need to close this diagonal off. Here we can explicitly create a filter for that node number. We can represent the sketch supports easily in our model. We will define 3 load cases: self-weight, vertical loads, and horizontal loads. We will start with self-weight. This was covered in the previous video. We can follow the same procedure for vertical loads and horizontal loads, except we will include no gravity in these load cases. Let's add the sketch concentrated loads to the structure. We will define a variable Q and add this Q in our nodal load, assigning it to the node numbers 2, 4, and 6. Remember, we need to convert kilonewtons to newtons. We'll add the horizontal load to node 2. Setting up the analysis and calculating everything. This is just as per the cantilever example from the previous video. By interrogating the results, we can see through the bending moments that the truss isn't acting as intended. Under the assumption of a pin-jointed truss, we should redefine the beam types as truss-only axial members. In the loop, where we define the members, we can simply add the member type designation member.trussOnlyN as opposed to the default member type. When doing this, the order of parameters changes. Refer to the documentation for the required order. We can also change these sections since we have grouped the different members accordingly. Remember, the string input is as per given in the RFEM section database. Now the structure is complete and the definition is as per the sketch on the right.